All right, so let's do section 2.3. So we're going to do volumes of revolution. We're still finding volumes using a different method. And this is going to be called the shell method or cylindrical shells. So before this, we did volumes using the general slicing method. That was like that loaf of bread that we were slicing things up into smaller pieces to find their volume. Then we started doing volumes of revolution. We did the disk method. So we started revolving regions around either the x-axis, the y-axis using the disk method. And then we did where we had a gap in the middle, which would have been the washer method, very similar to the disk method. The disk and washer were very similar, revolving things around x-axis, y-axis, or other straight lines using the disk method or the washer method. So now we're still going to do volumes of revolution. So we're not slicing like a loaf of bread. We're still doing volumes of revolution, but using now a shell method instead of a washer method. So another way to find the volume of a solid is to break it up into smaller shells, oftentimes called cylinders. It kind of depends upon your preference, rather than cross sections. So if I were to think about some shaded region that I see here in this picture, I can shade in that region, and then maybe just take one little sliver of that shaded region. And let's say I wanted to pick it up and revolve it around the y-axis, for example. And if I were to pick that sliver up and revolve it all the way around the y-axis, you can see that that sliver turned into a perfect right circular cylinder, or like a Pringles can, if you will. So that's what that looked like. And then if I were to do that for all of these little slivers, you might want to think of it like a nesting dolls, like one doll inside of the other, if you've ever seen those. And so then I have a whole bunch of cylindrical shells, one inside the other, so they're nested all the way through that solid. And I can just find the volume of each one of those pieces and add them up. And then just like we did for Riemann sums, just like we did for volumes in the general slicing method, you want those little slivers to get smaller and smaller and smaller. You technically want to do infinitely many. That's where the limit comes from, which then using Riemann sums is where the integral comes from. All right, and so that's what we have. So this is called the shell method. So let's say f and g are continuous functions with f bigger than g. Let's just assume one of them is bigger than the other. And then that region is going to be revolved around the y-axis. Let's find the volume. So I'm going to go back and look at that picture that I have up here. So I have f of x over there on the left. Let's just add in a second one. Let's call that g of x, shall we? And then now my sliver is just a little bit shorter because I now have something a little bit smaller. Here's my little bit shorter of a sliver, but I'm still going to, let's say, revolve that around the y-axis. And if I do that, you should be able to see that cylinder that it created, just a slightly shorter cylinder, but still a cylinder nonetheless. And we're going to try to find the area of that cylinder, and then we'll add up all infinitely many to get to the volume. That's where the integral is going to come from. So in this case, instead of the area of a circle, that's pi r squared, I now have an area of this entire cylinder, which is a surface area. So you want to think of it like that Pringles can that we're trying to find the surface area of that cylinder. So I'm going to write that down right here, just the word surface area, so that we can remember what we're calculating. I'm going to try to find the surface area of that right circular cylinder. Okay. All right. And so the surface area of a cylinder it's going to be the circumference of that circle times the height, which is 2 pi r h. Okay, and so then in this particular case, 2 pi is just 2 pi. The radius in that picture that I've drawn is still going to be from the center to the edge. So that would be from the y-axis to the edge. That's just simply an x value, right? And so each one of those cylinders, because we're going to have nesting dolls one inside of the other, each one of them are going to have a radius of some x value. So in that case, that is going to be a 2 pi. The radius will just be an x value. And then I need the height of that cylinder. And if you look over there at that picture, the height was from the top to the bottom. How do I find the distance between two things? You still subtract them. So that would just be the bigger minus the smaller, which would be f of x minus g of x dx. And it might be dy depending upon how we do that revolution. And we'll see some examples of that along the way. But that's going to be our shell method. The general idea of the shell method, like I said, it might be a dy eventually. So let's pay attention to that as we draw the pictures. All right, so think of it as, and this is a small typo. I should fix that. It's not really the volume of a cylinder. It's certainly the surface area. So let's fix that. That's the surface area, okay, of the cylinder, which we had written correct above. All right, so let's do an example. Now, before I do this example, I am going to visualize that in CalcPlot 3D so you can see what it might look like. Here's an example of some shaded region there on the left in 2 dimensions, and then there on the right, I'm going to do a revolution. I'm actually going to revolve that in 3 dimensions. And if I start to rotate it, you can look at that little sliver that I have there, and let's just revolve that one little sliver across the y-axis. And hopefully you can see there that that really did create a shell or a cylinder. That definitely created a Pringles can or whatever you might want to think of that as. And then that's what it is that we're revolving all the way around. And that was just one sliver. Of course, we're going to have to do that for all of them. And you'll see that this is going to be that 3-dimensional solid that we have created. All right. And it might be worthwhile for us to also visualize the many different ones. Okay. So let's say I have a whole lot of different shells there. And if I were to revolve those, let's say around, you can see one of those revolved all the way around, and then all of them revolved all the way around. Hopefully you can kind of see. That's hard to visualize, I know. Sort of the cylinder inside each cylinder, and we're adding each one up, and that's how we're going to find the volume. Okay, so that's the general idea. Let's draw the picture and do the calculus. So step 1 is always to draw the picture. All the time. Step 1 is to draw the picture. So R is the region bounded by y equals x squared. So I'm going to first graph y equals x squared. Pretend I'm a good artist. There we go. Here is my y equals x squared. I also have y equals 0. And y equals 0 just is that x-axis. And then I also have x equals 1, which is a vertical line, and x equals 4, which is also a vertical line. So you can see this is the shaded region in question. And I'm going to pick that up and I'm going to revolve it around the y-axis. This question is asking me to revolve that around the y-axis. So that's what we're doing here. I'm going to try to revolve that along the y-axis and see what happens. In this case, I'm going to draw a sliver. I'm going to choose, in this case, the vertical sliver, because if I look at that vertical sliver and try to imagine me actually picking it up out of the screen and revolving it around the y-axis, you can see that that is going to very literally create this cylinder. That one particular one's kind of short, so maybe like a tuna can, but it's definitely still created a cylinder or a shell. Okay, and so then with that shell in mind, I'm going to redraw that so it's maybe a little bit smoother. It's not the greatest one I've drawn. I'm going to pick that up and revolve it all the way around. There, slightly better. It's still not super great, but that's the shell that I'm revolving it all the way around. Okay, and I'm going to now try to find the surface area of that shell. And then when I add all of them up, which is the integral, that will become the volume. So the volume is going to be the integral of 2 pi RH. Think of it in always as 2 pi RH. Try not to think about it as this memorized crazy formula that has some bounds. That's a lot to memorize. I wouldn't recommend you memorize that formula. I recommend instead, because that formula won't always work, by the way, but this will always work. It's the 2 pi RH, okay? It's 2 pi for sure. And then R is going to be the radius of that shell and then the height of that shell. And so that's going to come from the picture, which sometimes it'll look like this formula, but sometimes they're not always called f of x and g of x, and you might have things tilted on their side, so you don't always know. But what you do always know is that the surface area of a cylinder is 2 pi RH, okay? So that's what we're going to do. So I have the integral of 2 pi RH. My radius, in this case, if I look at that cylinder that I have in red over there, the radius is from the center to the edge, all right, which is just an x value. That just is the x value, and I'm going to add up all infinitely many of those slivers, so the x's are all going to go from 1 to 4. So my radius was just x. Now I need the height of that cylinder, and the height of the cylinder is actually physically drawn right there. The radius isn't always physically drawn. That's harder to see, but the height really is just drawn right there. It just goes from the x-axis to the parabola, which is a y value, and that is the y value hitting the y value of x squared. So that really did just become the height of x squared. Sorry, that didn't mean to be erased. There it goes. And then I had the dx because I chose the vertical sliver. If I had chosen the horizontal sliver, it would have been a dy. Okay, then I'll simplify that. That becomes the integral from 1 to 4 of 2 pi. And in this case, it's nice and easy. I don't even have any adding, subtracting, foiling, anything too crazy. That's just an x times x squared, which just is an x cubed dx. And it only asked me to set up the integral. It didn't ask me to solve. So ta-da. All right, let's do another one. Let's see if we can get a few more examples. I won't do all of them, but let's do as many as we can to try to visualize what's happening. So same thing here. This one's only asking me to set it up rather than solve it, so that'll make it a little bit easier. So R is the region bounded by y equals x squared, y equals 0, x equals 1, x equals 4. Set up an integral that would find the volume of the solid generated when it's revolved around the line x equals -1. So just like before, step 1 is to draw the picture. Okay, and I've got still the y equals x, so it looks like it's the exact same region as before. So here's my y equals x squared. I chose to only draw it in the first quadrant, only because I know I'm bounded by positive x values, but you've got options here. And then I have x equals 1 and x equals 4. Here's my 1 and 4. And y equals 0 is the x-axis, so that's taken care of there. Here is my shaded region. I'm going to pick this up and revolve it, not about the y-axis anymore, but now about the line x equals -1. So I have shifted over. I'm going to draw that in a dotted line, and now my center has shifted. Just like in the disc and washer method, anytime your center has shifted, it's the radii that change. So the radius is changing. The height of the cylinder is still a height of a cylinder, and I'll draw that so you can see it. But it's the radii that is going to change because I've shifted my center. So let's draw a sliver. I'm going to choose in this case to draw, it looks like the vertical sliver is going to be the sliver that gives me that shell, and we're doing the shell method here. And in this case, it's just kind of a lot bigger of a shell because I've revolved it all the way around the line x equals -1. It's still a cylinder though, okay? So I'm still doing the shell method because I created a shell. So the volume is going to be 2 pi times the integral. Now 2 pi is a constant multiple, so I just factored it outside the integral. That's all I did there. And then I'm going to need the radius and then the height. And I'm still going to recommend that you label the radius and the height because that will help you remember that it's always going to be visual. It's a radius and a height, and you have to look at it and find the radius and the height. And the formulas aren't always going to be perfect. It's all going to come from the picture. That's what will always be perfect. It's visualizing that radius and height. So in this particular case, the radius is going from the center to the edge. So it's not just x anymore. It was x, the radius was x when I was revolving around the y-axis, but now I'm revolving around the line x equals -1, so my radius has shifted. It was x, but then I need to find the distance between x, which was the edge, and my center, which was -1. So that really is an x plus 1, or I'm going to write it as an x minus a -1, because you'll see that it is a distance, means you just take one minus the other. The bigger minus the smaller. This one was x, and then this one was -1. I just subtracted the two. X minus, so that sliver there was always x. That sliver was touching the x-axis, so it was x, and then I just did x minus a -1. Okay, and then the height is still the height. So the height is literally just straight from that picture, from that shell that you drew. The height is just going from the x-axis to the parabola. So that parabola really truly is just x squared. And then I chose the vertical sliver, which is a dx, and my bound in this case went from 1 to 4 because my x values went from 1 to 4 for that shaded region. And then I'll simplify. This became 2 pi times the integral from 1 to 4 of, this became x cubed plus, I think, there we go, yeah, x squared. The two negatives canceled and really do become a positive. And this one only asked me to set it up as well. It didn't ask me to solve, so ta-da. All right, let's do a little bit more. Let's see if we can practice a few more. I'm going to skip example 17. I encourage you to practice that one on your own, but let me look at example 18. Let's work through this one together, see how far we can get here. So let R be the region bounded by y equals 4x cubed, x equals 4, and y equals 0. Step one is to draw the picture. When in doubt, draw the picture. It's all going to come from the picture. So I have y equals 4x cubed. Hopefully we know what that graph looks like, but of course you could use your graphing calculator if you need. There's my y equals 4x cubed. I also have x equals 4, which is a vertical line. Here is my x equals 4. And y equals 0 just is the x-axis. So that's taken care of there. And here is my shaded region. Okay, let's read the question one more time. I'm looking to find the volume of the solid generated when this region R is revolved about the y-axis. Okay, so I'm going to revolve this about the y-axis. This question's a really great one, though. It asks you to use both the shell and the washer method. So let's practice two different ways to get the same answer, which is really common in all kinds of math and science. There's more than one way to get to the same thing. And sometimes one way is going to give you intuition for something different, and you might learn something new and be able to apply it to something different. So it's always good to be able to know more than one way. So here's an example of that. So here's my tip for you. Every single time you're finding the volume of revolution, no matter what method you're planning on using, choose the sliver first. And then the sliver is going to draw the object. That sliver will tell you what method to use. Okay, because it's going to be this little small sliver that we're going to create either a washer or a shell. But choose the sliver first and let the sliver choose the method. So let me tell you what I mean by that. I'm just going to start off with my quote unquote regular sliver, this little vertical dx sliver, and I'm going to be a little dramatic about it, but there I have it. All right, and then later on, I'm going to duplicate this picture, and maybe you'll want to pause this video and duplicate it yourself as well, because we are going to have to rework some of this stuff in two different ways. So I'm just duplicating this entire picture, and then I'm going to choose later on the other sliver, which would be the horizontal sliver. So just do one at a time. I really am going to just do one at a time. Maybe we'll even draw like a little squiggly line here. We're going to separate those two. And let me zoom in on the first option and see if I can figure out what method that is. Right now, off the top of my head, I can't tell which of those pieces is going to be the shell method and which one's going to be the washer. I can't tell. I have to actually physically draw the revolution. You have to at least see it in your head. You have to at least see it in your head. And that takes time. It takes some time. So this first one, if I chose that vertical sliver and I'm wanting to revolve around the y-axis, if I were to pick that up and revolve it around the y-axis, hopefully you can visualize that that created an entire cylinder or shell. So that had to be the shell method. So for that example, for that sliver choice for this example, it's the shell method. Once I know it's the shell method, I know it's going to be volume is 2 pi times the integral of the radius times the height. Notice how the way I said that without memorizing a formula, it really is just 2 pi times the integral of the radius times the height. Now again, the sliver chose that method, shell method, and in this case, that sliver was a vertical sliver, which is a dx. So my bounds are still from, was it 1 to 4? I'm sorry, I should scroll back up. I think it said, no, it didn't say 1. This one did not say 1. It was just the x equals 4. So it wouldn't be 1 to 4. Sorry, it was all the way down to 0 to 4. Okay. Always read the question for sure. All right, so now I need to find the radius in this case when I'm revolving this around the y-axis. To find that radius, I should be able to see that this from the center to the edge is just simply the x value, right? That sliver right there that before I did the revolution just touched the x-axis. So the radius is x. And then the height is straight from this picture. It goes from the x-axis to that cubic function. So that height was just 4x cubed. And then I suppose I could simplify that. So 2 pi times the integral from 0 to 4 of 4 times x to the 4th dx. And we might as well calculate that. Let's get an actual answer for that. So this is 8 pi, because 2 times 4 is 8. And then I can integrate it. X to the power of 5 divided by 5 from 0 to 4. I can plug in a number, and I got 8192 pi over 5. If you're willing to, I just typed it into my calculator. I really did just type it into my calculator. I did 4 to the 5th times 8. Hopefully I typed it in correctly. All right, so that's what I got. Ta-da. Cool. Oh, and I think that's fair. Yeah, let me show you exactly how I typed that in so you guys can see what it is. I didn't use pi in my calculator at all. What I did was I did 8 times the 4 to the power of 5, and I just did that, which was the 8192, and then it was the divided by 5. And if I do the divided by 5 and click the math fraction first, that will reduce the fraction if it does reduce, which it didn't. Okay, all right, so now I have that, and maybe we should add in really quick units cubed to remind us that we were finding a volume. Okay, so now I did the shell method, and anytime you're telling me you're solving these problems, you need to tell me what method you're using so I know what it is that you're calculating. Okay, but this one did say to use both methods, so I have to use the other. Now, again, I didn't know that that first one was going to be the shell method. I didn't know. I just drew the sliver. And then the sliver happened to be a shell, so cool. So now I choose the other sliver, and let's see, does the other sliver give me a washer method? So in this case, I'm revolving that sliver. I'm going down to that second picture now, and now I have the horizontal sliver. Can you imagine me picking that sliver up and revolving it about the y-axis? How that would then create ooh, that's not a good picture there. How that would then create a washer. Ooh, that's not great picture, but can you kind of imagine that's a washer or like a flat donut, but on its side, you're looking at it at a side angle there. So that is definitely going to be a washer method. So now that sliver chose the washer method for me. So because it's the washer method, I know it's going to be pi times the integral of big R squared minus little r squared. And in this particular case, that sliver happened to be a dy sliver because it was horizontal. You saw in the previous video that sometimes we used a washer method with a dx. Like there isn't one formula that works. You really got to draw the picture. That's the every single time draw the picture. Okay, so then I got to do the big radius and then the smaller radius. So the bigger radius you should be able to see is from the center to the edge. It looks like the outside was that 4 right there. So that outside the bigger radius was 4. And then the inside radius was definitely this cubic function. But because remember we're doing dy, I needed to rewrite that equation to be an x equals. So it was actually going to be the cubed root of y over 4, which you could write it as to the power of 1/3. Okay, and then my bounds would be from 0 to something. How do I find that something? So the bounds are from the shaded region, and because I'm doing a dy, the smallest y value of that shaded region was 0. The highest y value is going to take a little bit of work, but it's actually quite simple. In this case, y equals 4x cubed and x equals 4. You can't set those two equal to each other, all right? Because that bottom one was an x equals 4. You can't set an x equals to a y. So you have to instead plug in x equals 4 into there. And I would end up with a y equals 4 times 4 cubed, which is 256. And that's where the upper bound of 256 comes from. Okay, now let's simplify. We got to do the calculus, the integral from 0 to 256, so 16 minus. This is going to become y to the power of 2/3 divided by 4 to the power of 2/3 dy. And then I'll do some calculus here. Pi times the antiderivative of 16 is 16y minus, and then that 1 over 4 to the power of 2/3 is just a number. It's just some number, so I get to leave it there. It's a constant multiple, it can stay. But I would add 1 to the power, divide by the new power. So y to the power of, I add 1 to the power is going to give me 5/3, and then divide by 5/3. Evaluate from 0 to 256. Simplify along the way and use your calculator if you'd like. But I still got 8192 pi over 5. I'm not going to bore you by making you watch me plug that into my calculator, but you can use your calculator. Point is, we got the exact same number as we did before. right? So two different methods to give you the exact same thing because it was the same question. It was the same solid that we found the volume of. We just did it using a different method. Ta-da! All right, let's do another example. Let's do another shell method example. I think it's gonna be worth our time to set up at least a few more. So let's say R is the region bounded by y equals this guy, which is 1 over the square root of 9 minus x squared, and the x-axis over this interval from 0 to 5 over 2. Find the volume of the solid generated when R is revolved around the y-axis. All right, let's go ahead and draw the picture. Step 1 is to draw the picture. Your picture does not need to be perfect. But you do need to have a general idea of where the picture is because you're going to have to draw your sliver. You're going to need to find your bounds. You might need to know like a bigger and a smaller, all of that stuff. So you do have to have a general idea, even if it isn't perfect. So feel free to use your graphing calculator. I'll go ahead and use my graphing calculator. You might be using Desmos if that's what you have. On a test, you'll have to use a graphing calculator. So make sure you get used to how to use your graphing calculator. I'll go to my y equals, and it's 1 divided by and it looks like it's the square root. Let me find that. The square root of, was it 9 minus x squared? 9 minus x squared. Okay, and then I'm going to go to graph. You might have to go and find it there. Whew. That does not look great. I have to zoom in a little bit. My graphing calculator probably looks a little bit different than yours, but hopefully have a general idea. All right, and this is the general shape of that graph. So now you have a general idea. Kind of looks like a weird flattened parabola, it looks like to me at least anyways. So let's graph that. It certainly doesn't need to be perfect, but just the general idea looks a little something like this. Okay, so here is my y equals 1 over the square root of 9 minus x squared. And I have an interval. In this case, that interval is from 0 to 5/2. When an interval is given to you, you can assume it's x values, unless you're told otherwise. Okay, all right. So, and it's bounded by the x-axis as well. So it looks like this is my shaded region, and I'm going to revolve this around the y-axis. I still like to draw that arrow to help me visualize and remind myself which way I'm revolving. And then just as to find the volume. So it doesn't tell you what method to use. You get to choose. But remember, here's my tip. You don't choose the method. You choose the sliver. You really don't. You choose the sliver. The sliver chooses the method. Okay? So I'm going to just pick a sliver. And the first thing I'm going to do is I'm going to show you the wrong sliver. So that way you know what it would look like if you chose something that looked weird and didn't quite work out. So if I were to choose a horizontal sliver, you have to remember something. There are infinitely many slivers. So like there are all of them. You have to like literally visualize all of the slivers across the entire shaded region. And I hope now that you see that, you can see why this was not a good choice for my sliver. Because it looked like some of them were bounded by the two graphs, the 5/2 and the parabola. But then some of them never even touched that parabola. So that would be two different integrals. That's not great. So I want to choose the sliver that's going to be a little bit easier. So let me show you now the correct sliver. Now, how do I know it's correct? Because I already knew the answer to this one, but this is what you would do. You would try, well, let's try the other one and see what happens. And you have to remember that there are infinitely many slivers. So you don't need to draw all of them, but you need to have them in your head. And in this case, does it look like all of those slivers have that weird parabola on top? And they all have the x-axis on bottom? Yeah, so that's like a good choice for a sliver. So I'm going to take that sliver and I'm going to choose just one of them. I'm just going to choose one of them. I'll choose the first one. In this particular example, the question asked me to revolve this around the y-axis. I don't have a choice in that one. So when I revolve this around the y-axis, did that sliver create a washer or did it create a shell? That created a shell or a cylinder. It might have created a washer or a disc if it were revolved in some other way. Like you really don't know. There is not a one size fits all. There really is not a one size fits all. You have to actually look at the sliver and visualize it. What does it create? So this sliver I chose the sliver. I chose, in this case, the vertical sliver. The sliver chose the method. This sliver chose the method. In this case, it was a shell method. Okay, now we have everything we need. Now that I know it's shell method, volume is 2 pi times the integral. of the radius times the height. I chose, in this case, the vertical sliver, so that's a dx. So my bounds should be from the x-axis. And then the radius of each of those shelves was just simply the x value. Nothing was shifted. And then the height really went from the x-axis to that parabola. And in this case, it was that weird function, 1 over the square root of 9 minus x squared. Okay, and then we simplify so that we can evaluate it. So now I have a 2 pi, the integral from 0 to the 5/2, sorry. And then I'm going to rewrite that as x times 9 minus x squared to the negative 1/2 dx. I'm going to go through and evaluate this whole integral for you guys. It should feel similar. This is a Calc 1 review now, but we can do it. There's no way I know that antiderivative off the top of my head. Here is a classic example of a u sub, where I am going to let u be the 9 minus x squared, and then du was negative 2x dx. So du divided by negative 2 was x dx, and I'll highlight so you can see where I chose that from. My problem had an x times a dx, so I wanted an x dx by itself, which is why I divided by a negative 2, and now I'm going to end up with a du divided by negative 2. We can do it 2 pi times the integral u to the negative 1/2 times du divided by negative 2. Let me point this out one more time. If you're watching, be really careful with this. It was the x and the dx together that got replaced with the du divided by negative 2. And then the other thing that was left over was just this 9 minus x squared to the power of negative 1/2, which just was u to the power of negative 1/2. Okay, all right. And then I had a new bounds because I have a new variable. So I'm going to go to my u sub and figure out, plug in my old bounds into my new bounds. If I plugged in 0, I would get 9 minus 0 squared, which is 9. Excuse me, if I plugged in 5/2, I'll show the work, it would be 9 minus 5/2 squared, which is 9 minus 25 over 4, which is 11 over 4. So you can use your calculator, of course. So then I have, my bounds are now from 9 to 11 over 4. Okay, and then we do some more integration. So I have a pi, the 2's canceled, the integral from 9 to 11 over 4 of negative u to the negative 1/2 du. All I did is those 2's canceled, but the negative did not. That was it. And then I'll just keep on going. I'm going to keep going with this integration. So negative pi, I just brought the negative outside the integral. You're allowed to do that. And then I'm going to do u to the u, add 1 to the power, divide by the new power, evaluated from 9 to 11/4. I'm going to simplify this even farther. Now that becomes a negative 2 pi u to the 1/2. And I'm going to highlight where that comes from. When you divide by a fraction, you multiply by its reciprocal. So that would be times 2. So negative pi times 2 was the negative 2 pi. Okay, and I know this one's getting a little bit ugly, but I really am going to work all the way through it. I really think it's going to be worth our time. I'm almost out of space. So negative 2 pi times 11/4 to the 1/2 minus a negative 2 pi times 9 to the 1/2. So then I have a negative 2 pi square root of 11 divided by the square root of 4. And then plus 2 pi times the square root of 9. Okay, so this turns out to negative pi times the square root of 11 plus 6 pi. And if you wanted a decimal, you're welcome to type that into your calculator and round to whatever maybe your homework might be asking for, or a test or quiz might be asking for. But exact answers are preferred unless you're told to round. Units cubed. Ta-da! Whew, a little bit trickier. Not so bad. It could be worse. Could be worse. Let's do another one. Let's do another one. I'm going to skip that next example 20, but the next one I'm going to do is the one that has a trig. We haven't done a trig one yet. Let's do example 22. Okay, same type of question. We're still just talking about a whole bunch of practice of finding volumes of revolution. Okay, so set up an integral. In this case, I am told to use the shell method. So I have to make sure I choose the correct shell or the correct sliver that will give me the shell. that would find the volume generated when the region bounded by the curves x equals cosine of 3y, x equals 0, y equals 0, and y equals pi over 6 is rotated around the x-axis. So, as before, step 1 is to draw a picture. Let's draw the picture. This one's a little bit trickier. Your graphing calculator might not be as helpful. It might be, but you still have to use a little bit of your understanding of what it means to have an x equals. So an x equals cosine of y is everything is switched, right? So x equals cosine of 3y. Feel free to use Desmos if you need, but hopefully you can graph the y equals cosine of 3x in your graphing calculator and then flip it on its side. But either way, I'm going to draw that hopefully in a different color. Here we go. So it's going to look a little something like that because cosine started up at 1 and it's not perfect, but it's something like that. That's my x equals cosine of 3y. And I also have, what else do I have? X equals 0. X equals 0 is the y-axis, and y equals 0 is the x-axis. So this would be my shaded region, and I'll label this so we remember that intercept really is the y value of pi over 6, not just because it told me, but because I also just know where this touches the y-axis. Cosine of 3 times pi over 6 would be cosine of pi over 2, which is 0, so that's how I knew that. Okay, but either way, there is my shaded region, okay? And in this case, I am revolving that around the x-axis. So I got to pick that up and revolve it around the x-axis. So let me just draw a sliver and see what happens. All right, I'm going to just draw my quote-unquote regular sliver. That's always how I start because to me, that's the first thing I learned. So it's always the first thing I think about. And that might be a strategy that you use as well. And I'm going to pick that sliver up and I'm going to revolve it, around the x-axis. Let me draw that picture. I'm going to revolve it around the x-axis. So I'm going to pick it up and revolve it around the x-axis. And you might see that if I did that revolution, if I picked it up and revolved it around the x-axis, that did not create a shell. That created a disk, right? Not even a washer, a disk, because it had no empty space in the middle. So this created a disk, but I needed a shell method. So that was probably no good. So what you have to do is you have to try the other sliver. The sliver chooses the method. So you have to try both slivers until you find a sliver that you need. And in this case, I needed the shell method. So the vertical sliver did not work. Let's try the horizontal. I'm going to draw that horizontal. I always draw it really thick just to be dramatic on the video. You might just draw a single straight line. Totally fine. But here's my now horizontal sliver, and I'm going to pick that up and revolve it around the x-axis. And as I revolve that around the x-axis, can you visualize there that that sliver did create the shell? So here we are doing the shell method. We got it. So the volume is 2 pi, the integral radius times the height. I had to use, in this case, I had to use the horizontal sliver, so it's a dy. So my bounds would come from the y-axis. And my radius is now a y value because my sliver now is y. So my radius is y, and the height is the x value. Take a look at this. Is just a cylinder on its side. That's all it is. It's just a cylinder on its side. So that is an x value. And it goes and it touches the cosine graph. So x equals is where I'm going to get now the cosine of 3y as the height. Maybe we should label that to be consistent. Here's my radius. Here's my height. Okay, and here's another example. This one only said setup. I didn't say to solve, so that's it. It didn't ask me to solve it. Sometimes you're going to be asked to solve, sometimes you're not. So make sure you read the question. That's all there was for that. Ta-da! Okay, let's do another one. I have another one for us to do. I'm going to skip around a little bit. I'm going to do, I think it was going to be this one. No, I'm going to do 24. Okay, I can't do all of them, but let me do example 24 so you guys can visualize it. They're all going to be very similar. Draw the picture. It's all going to come from the picture. R is the region in the first quadrant. Let's draw the picture. Only in the first quadrant, which is nice. Bounded by y equals x squared, which I know you know what it looks like. Here is my y equals x squared, and I have y equals 4. Y equals a number is a horizontal line, and x equals 0 is the y-axis. So then this is my shaded region, and I want to find the volume of the solid generated when this region R is revolved about the line x equals 6. So way over here, here's my x equals 6. It doesn't say what method, so I could choose any method I want. But remember, you don't really choose the method. You choose the sliver. The sliver then chooses the method. So I get to just choose whatever sliver I want. I don't really know. Sometimes one's easier than the other, like we saw before. If I were to choose a vertical sliver, and then I were to do that revolution, to me, I can visualize that. That definitely is creating a shell. I think shell method is totally fine. All right, totally fine. I also can see that if I were to do a horizontal sliver, if I were to do that horizontal sliver, then that would create, it looks like a washer. Also fine. I don't really see one problem versus the other. So I'm just going to choose let me pick the color. There we go. I'm going to choose the vertical sliver. And maybe you're going to retry this on your own using the horizontal sliver, using the other method. It doesn't matter. That sliver in this case created a shell. So we are going to choose to do, oh, this one does say use the shell method. Oh, how funny. I didn't even notice it said that. Really sorry. This is on the video. Oh, well. Good thing I chose the shell method. But you might have some examples later on where you can choose which method to use. So keep that in mind. Sorry about that. We'll get there. All right. So my shell method here, volume is going to be 2 pi times the integral of the radius times the height. And I, in this case, have the vertical sliver, which is a dx. So my bounds are going to go from 0 to 2, not 0 to 6. Why? Why? Think about it. It's always going to be from the shaded region. Your bounds come from the shaded region. So the lowest x value and then the highest x value. To find that highest x value, I just set those two equal to each other. X squared equals 4. I could do that in my head, and I just got the x value of 2. Okay, and now I need the radius. Now the radius is, again, from the center to the edge. My edge, when I was doing that vertical sliver, was x. And so from the center to the edge, you do bigger minus smaller. So in this case, that really is 6 minus x. And then the height is going to be, like, you literally see the height right here, but it looks like it touches the y equals 4 and it touches the parabola. So it's bigger minus smaller. When the center is shifted, your radius changes. The height, no matter what height, the height is never going to have anything to do with the center, ever. The height is always just going to be like bigger minus smaller of the actual sliver itself. So let me label those so we have that. Here is your radius. Here is your height. Okay, and then let's find the volume from there. So now I have a 2 pi times the integral from 0 to 2. I'm going to have to FOIL and see what happens. I have a 24 minus 6x squared minus 4x plus x cubed dx. I'll do that antiderivative. 2 pi was on the outside of the integral, so don't forget it stays on the outside of that parentheses. So 24x minus 6x cubed over 3 minus 4x squared over 2 plus x to the 4th over 4 evaluated from 0 to 2 and plug in my bounds. So I would get 2 pi times, if I plugged in 2, I got 48 minus, it looks like I got 6 times 8 over 3 minus 4 times 4 over 2 plus 2 to the power 4, 16 over 4. And then minus, in this case, when I plugged in 0, I got 0. And of course, feel free to use your calculator if you'd like. And I got 56 pi units cubed. Ta-da! All right, so I did have a nice little summary here for you guys to just quickly visualize it. I just took it straight from a textbook. Just to visualize a general idea of the pictures, notice how it's the sliver that chooses the method. Okay, so sometimes your sliver is going to choose the washer method. Sometimes that vertical sliver is going to choose the washer method. Sometimes that vertical sliver is going to choose the shell method. It depends upon what you're revolving about. So you have to also think about what you're revolving about. A vertical sliver revolved around the x-axis, created that washer. A vertical sliver revolved around the y-axis, created a shell. And then a horizontal sliver A horizontal sliver revolved around the y-axis, created a washer, whereas a horizontal sliver revolved around the x-axis, created a shell. So rather than just memorizing a whole bunch of formulas every time, draw the picture, think about the sliver, visualize what object that sliver is creating. Is it creating a washer, a disc, or a shell? And then think about washer is going to be pi times big R squared minus little r squared. And then shell is going to be 2 pi times the radius times the height. And anytime your center is shifted, whether you're doing washer or shell method, if the center is shifted, it's the radius that changes. All right, so that's what we got for the shell method. Thanks, everybody.